Software Engineering Radio, episode 84, Dick Gabriel on Lisp. So, listeners, welcome to another episode of Software Engineering Radio. This is another episode we're recording at UPSLA 2007. And actually, we're talking to Dick Gabriel, who is the chair of UPSLA 2007. So, welcome, Dick, to the show.
Glad to be here.
Thank you. And first of all, thanks for organizing this conference. I found it really nice, so thanks for all the work you've put in.
Yeah, it's a lot more work than the general chair is led to believe at the beginning. I've been working on it for 128 weeks.
Wow. Sounds really like a lot of work. So you were also the person who made these rooms available to us, so thanks again for that.
Okay, good. I'm glad you could use them.
Yeah, absolutely. So why don't you introduce yourself to our listeners a little bit?
So my name is Dick Gabriel. My background is some degrees in mathematics, then artificial intelligence at Stanford University. I worked with John McCarthy at Stanford for a few years. I started my own company. After that, it was a Lisp company called Lucid, and it existed from 1984 to 1994. After that, I went to Park Place Systems, where I did more management stuff by sort of accident. I originally went there to write a book with Adele Goldberg, and then they had some development issues, and sort of to see whether the reason that I felt that I was fairly effective at Lucid was that I was the person who hired everyone. I wanted to see whether that was true or false. So I helped them out. Then after that, I went back to school and got an MFA in poetry.
Right, and we'll talk about that later a bit.
Yep. And then since then, I've been at Sun Microsystems and now IBM Research.
Okay, cool. So you also already mentioned the topic we are going to focus mainly on in this episode, and that is Lisp.
Yep.
So why don't you give us a little introduction, Lisp in 3 minutes. What is it all about?
So Lisp has a couple of interesting features. One of the earliest languages. It was developed, this is its 49th birthday this year.
Cool.
The core of Lisp is a functional language, which means that everything in the language is a function, which means it takes arguments and returns a value. And then the way computation is done is by nesting functions. So you call a function with some arguments, it returns a value, and that value is the argument to other function calls, et cetera, et cetera. It's interesting because the data structure, the primary data structure, but not the only one, the list, is also the data structure that encodes the programs.
Right.
And so programs and data are the same, so you can construct Lisp programs using Lisp programs and execute them at the same time. And that was thought to be how artificial intelligence would work. You'd have a program that was artificially smart. It would construct programs on the fly and execute them and thereby learn or be told things. Since then, that's from the early 1960s, since then it's developed into a full-fledged kind of a systems programming language. So it was an early it had early implementations of threads. Threads, there's built-in compilers within the runtime, memory managers, operating system interfaces. So typically Lisp programmers feel like they live inside of the language. They live inside a running execution of it, much as Smalltalk people do.
Yep. So in addition to having lists and functions as the main abstractions, other aspects that are important probably is side effect freeness, right?
As for the functional core, yes. But for the non-functional core, it's an imperative language. So you do have sequencing.
Oh, I didn't know that.
So you can do things. So there's a function called prog, which stands for program. And what the function does is it takes no arguments, and then what it does is it executes. It defines some local variables. It then executes a sequence of functions, one after the other, all of which probably have some sort of side effect, and then it returns the value of the last. And you can put labels in there and go-tos and stuff like that. It's called the program feature. There is an assignment operator. Now, Lisp is very famous for not using obvious names of things. So the assignment operator is called setQ, so set quote. The The reason that it's set Q, set quote, is that because it's fundamentally a functional language, everything is evaluated. So you need something that says, don't evaluate this. So, so in Lisp, if the Lisp interpreter sees a list, it interprets that as a function call where the first thing is the function, everything else is an argument. If you want that thing to be treated as a list, you have to quote it. Okay, so there are side effects. There are object-oriented extensions. There are arrays and complex numbers, and you name it. It's got hash tables, on and on and on and on.
So you already mentioned that Lisp has come out of the AI community.
Yep.
Can you talk a little bit about the mindset of how things were back then, why Lisp became the way it was in addition to just being able to construct itself? What was the grand goal? What was the context?
So the grand goal, and this is probably more my opinion than the accepted opinion, was that the artificial intelligence people were endeavoring to write programs that no one knew how to write. And so it was the idea that you could sort of sit down and say, well, here is my problem, here are the requirements, let me come up with a specification and now code that up. Completely crazy as far as the AI people are concerned. They want to sit down and write a program that demonstrates some version of human intelligence or human behavior.
Yep.
There's no idea. And so the only way to do it was to experiment. Well, let me try this. Let me add that. Let me try to add this fuzzy concept. Let me try to add scheduling. Let me add agendas. Let me add resources. Let me have resource limitations. And so the idea is you're constructing a system that you hope one day will show some intelligence, but you're not constructing it like making a ton of source code and compiling it periodically. You're constructing it the way you construct a city. You build some of it, and it's running all of the time. So it's kind of like a live programming language. I think that's because the task of, or the work of writing artificial intelligence programs is considered too far away from what people knew how to do.
So let's look a little bit more closely at some of the interesting features, and one thing that I'm particularly interested in is this thing that's programs as data and data as programs. So that was basically the first, let's say, implementation of meta programming.
Yes.
So can you talk a little bit about how this thing works? How do you do this? How do you how do you make a list to become a program?
There are several ways. So I'll tell you the classical way, and the other ways are refinements that make it work faster. So one of the things, John McCarthy was the guy who was sort of responsible for Lisp. He had the original ideas, and he had a team of some grad students, I think 6 grad students and a couple other folks, who were implementing it back in the the late 1950s, early 1960s at MIT in Cambridge, Massachusetts. And at that time, there was sort of a debate among logicians and mathematicians and computer scientists, but they weren't called computer scientists then, as to computability. So at that time, people were talking about Turing machines, the von Neumann architecture, and one of the concerns was universal computation. Was there a function, was there some mechanism that could compute anything that could be computed? So the Turing machine was considered that. Now, it was considered that, but with the program that the Turing machine ran, which was the universal Turing machine, which would take a description of any other Turing machine and execute it. And that was a big, complicated piece of code, basically. So what John McCarthy did was he said, well, using list structure and this functional kind of idea, the universal machine for Lisp is quite short. In fact, it fits on about 15 lines of code, and it relies on the fact that it's interpreting list structure. So when it sees a list, it looks at the first thing. If it looks like it's a function, it applies it. Otherwise, it uses rules. So if it's a conditional, it does the logic of that. It was a very short piece of code, and one day Steve Russell said, well, if I took that piece of code and I hand-compiled it, then that could be an interpreter for Lisp. And so he did that, and that surprised John McCarthy. And they overnight they had a running implementation of Lisp. When he thought it was going to be a many month, it took one night to implement this interpreter. And so when they saw that, they realized that they could use this universal machine, which they called eval,
Right.
Which is to evaluate a piece of Lisp structure or anything that Lisp has as a program. You could then construct any list you want and then hand that as an argument to eval, and then that would execute it.
Okay.
And so that was the beginning of it. And it just really surprised people that they could do that so easily.
Mm-hmm. So that's also this notion of the meta-circular interpreter,
right.
which is, I think, a really great geeky word.
Right, yeah.
So it's basically a program that, I shouldn't say interprets itself, but the interpreter is written with the same tools and languages as the thing it interprets.
Right. It took a lot of people a long time to understand the concept of meta-circular interpreter as kind of first introduced or first explained by Brian Cantwell Smith in the, I think, mid to late 1970s. Mm-hmm. So I mentioned that this universal function, eval, is written in Lisp.
Yep.
And so what Steve Russell did was he hand compiled it.
Right.
So you'd think, well, okay, so eval is written in Lisp. So that means that when eval is executing, it's actually executing itself.
Yep.
Okay. So there's this concept of you have a base level program, which is what eval is interpreting, and then eval is up one level, and it sort of looks at the Lisp structure and interprets it.
Right.
Now, eval is in Lisp, so you can imagine that it's at another base level, and that there's another copy of eval up above, and it's like that all the way to the top.
Yep.
So that's the meta part. Mm-hmm. It's circular in that the language that's implemented in is the language it's interpreting. Mm-hmm. And the trick, though, is at the top. You don't go all the way up forever. At the top, you need something like what Steve Russell did, which is a compiled version of it.
Yeah.
And so what that is it's a process that's exactly like what eval does, but it isn't eval itself. It's in something that the physical world can interpret.
Yeah, a C program.
It can be a C program. It can be machine language.
Sure.
Now, one of the tricks that people use, and you can confuse people who's extremely smart with this, is the way that a lot of interpreters are actually written is they write a Lisp compiler, mm-hmm. and then they write the classical eval, which is like a page or so of code, and then you compile it. So consider the definition of car. So remember I said that Lisp uses interesting names for things.
Yes.
So if you have a list, the first element is you can access it with the Lisp function whose name is car. Yep. So if I have the list 1, 2, 3, then car of that list, car of 1, 2, 3 is 1.
Yep.
So and that has to do with the contents of the address register. There's the original machine. And then coulter means give me the rest of the list, and that's contents of the decrement register. So it's using registers.
CDR, right?
Well, CDR.
CDR, oh yeah.
And then if you were going, so that gives you the rest of the list. It strips off the first element. If you want to strip off the second element, CDDR. If you want to strip off the first three, CDD. So you can have any number of these. So you can sit in front of a Lisp system and type in what's called S expressions, these lists that are interpreted as code. Mm-hmm. You can type them in, and they get evaluated right away. Yep. So you can type in car of, quote, 1, 2, 3, the list 1, 2, 3, and it works. Mm-hmm. So that means the function car has a definition, means someone wrote the code for it. Yep. So the definition that is actually used is defun. So defun is how you define a function. Defun car. It's the name of the function. Then you say it takes one argument, x, and then its definition is car of x. And you go, but wait, how can that work? Because it's recursive. Yeah. So you're defining the function car, and how do you do car? You call car. So if you keep on doing that, it's going to loop forever. Yep. However, what happens is the compiler sees this definition. Mm-hmm. It open codes, that is to say, it emits machine instructions when it sees car. Mm-hmm. It doesn't care that the name of the function it's compiling is car. Mm-hmm. And so when you define the compiler, you define a few things like car, how that compiles, coulter, how conditionals, et cetera, et cetera. And so these sort of meta-circular looking definitions look ridiculous because they all look like they're infinite recursive.
Yeah, but they're
loops.
resolved by the compiler.
And they're resolved by the compiler, which sort of bottoms out this or tops out this tower of meta-circularity. Cool.
Mm-hmm. One thing that is always, that some people consider a criticism of Lisp, others say that's really its essence, is that it basically has no syntax. I mean, you more or less literally write the syntax tree in form of lists.
Right.
So that also makes it possible that a user-defined function looks exactly the same as built-in stuff, which gets to this concept of growing a language that Guy Steele had in one of his famous talks that's online on Google Video. We'll put a link to it.
Listen to that.
We'll put a link to it in the show notes.
Good.
So can you talk a little bit about the idea of growing a language and how that plays into Lisp?
Yeah, so that was another extraordinarily important thing, which I believe was an accident, in that, as you mentioned, any function that is in Lisp, the syntax for using it is identical to as if a user did it, a person. Right. And then you needed some special other forms as well, so conditionals. So the way that Lisp interpretation normally works is you get a list, it looks at the first thing and says, it's a function. And then it evaluates its arguments. Then it passes those things as arguments to the function that is the first one. Right. So now if you have a conditional, so if you say, left parentheses if, then some predicate, and then if it's true and if it's false, two separate things. Right. Well, you can't do that way, because that would say, okay, I got if, so I evaluate all three things, the predicate, the true part, and the false part. But you didn't want to do the false part. Right. So you needed some sort of special form. So in Lisp, there are special forms that are interpreted specially, and users can define those using macros. Right. And so what this meant is, again, this endeavor of trying to write programs that people can't write, artificially intelligent programs. One idea that quickly came to the fore was Lisp is the wrong language for writing that program. I need a special program to play chess. I need a special program to understand mushrooms if you wanted a system to classify. I need a special programming language to understand surfaces. And so many AI researchers would start their research in some area, trying to make a program that's smart there, by defining the language first that they could express their concepts in. Yeah. And so they would immediately extend Lisp so that it would be easier to write the programs. And so a lot of artificial intelligence research in the 1960s, 70s, and early 80s was figure out roughly what you wanted to do, design the language for it, implement it in Lisp, which means that it's an extension to Lisp. So it's just defining functions and these special forms. Yep. And then write your great program. But then people would invent these great languages as grad students, and their advisors would say, well, that was a lot of work. And that language you devised was really interesting. Why don't you write that up as your dissertation? And so people would would start in some AI project for their PhD, and they would end up publishing a language definition instead. And
the funny thing was that, today you would say maybe that isn't really a different language. It's basically, we could call it a framework because it defines functions and procedures. Yeah. So it's a bit different from what people today consider language and DSL development, because there is no notion of adapting the syntax because everything looks like trees. Right.
And so the other nice thing is when you're a normal, let's say, language designer, you have to worry about the syntax, and though there's tools to make it really easy, you still have to worry about parsing. Right. You don't have to worry about parsing. So Lisp has this uniform thing. The first thing is either a special form or a function, and blah, blah, blah. It's just 15 lines of code. Yeah. So you don't have to worry about that. You just worry about the expressiveness of
what you write
of the stuff. Yeah.
I mean, if I were a critic or a cynic, I would say you could do this with XML today, and everybody would say, "Wow, that's ugly. You can't use because it's basically literally a tree." So I'm that limited set of primitives and doing everything the same way is very elegant, but it's not necessarily user friendly. If you consider a user to be some non-programmer, which is what DSLs tend to be focusing on.
Yeah, that's largely true. XML to me, maybe I'm naive about it.
Well, it wasn't a serious suggestion, right? It was.
But XML to me is verbose, and so you would have some left angle brackets and some complicated thing, right angle brackets, then blah blah blah, and then another set of angle brackets. And those angle brackets are really just left paren and right paren. So it's more compact. Yep. There are some systems. So, for example, the text editor Emacs is a very simple engine, and all of the commands that you do that users use are written in eLisp, dialect of Lisp. And they're not naive users who are using Emacs,
Sure, yeah.
but they're not AI people, they're not Lisp programmers, and so it's a very compact language, so you can write a lot of things. And so people less expert at programming in Lisp than you would think have found it effective. Normal people, no. Domain experts, no.
Sure,
so I agree with all of that.
Yeah.
The other thing that's about Lisp is Lisp has a type system. Some people think, Lisp is not a typed language. And I guess there's some controversy about the terminology. So what I learned in school was that the term strongly typed meant that no operation would be permitted to be carried out on arguments of the wrong types.
Right.
So that's usually interpreted as the compiler won't produce code for that.
Right.
In Lisp, that's interpreted as when you try to do that at runtime, it throws an exception.
What you're getting at is that there is a difference between strong and weak typing and static and dynamic typing.
Right.
So Lisp is a strongly typed, dynamically typed, strongly typed
That's
language.
right. Yeah. And so what that means, and this is useful for beginners, I think, because beginners would use BASIC, they would use Logo, they would use a bunch of other small languages like that, is their programs are not verbose because it's telling the compiler about types everywhere. The types sort of are done at runtime, and so how do you make X, the variable X, refer to a floating point number? Well, you don't declare that X is who's going to hold it, and then you type in the thing. You just say set QX to 3.14159, blah 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 blah, and then if you can ask at runtime, what is the type of X?
Sure.
What X refers to, it says, well, it's a floating point number. So that makes it a little more compact, which maybe might make it easier for end users. But again, I wouldn't say, let's try it on them. I mean, someone could try it on them, but it's not an argument I'll make.
Can you briefly explain what macros are? You already mentioned it while explaining some of the meta stuff.
So in most languages, so for your listeners, if you think of macros, it's a string type of operation. So you see some sort of pattern of string in front of you, the compiler does, and says, this is a macro, and it does a string substitution to what the macro means. So in Lisp, it's like that, only different. So what the interpreter does, and so the compiler mimics the semantics of the interpreter, suppose you define the macro Zatesh. And so and Zatesh is going to be a complicated control construct that's going to spawn a bunch of processes and monitor them in a particular way and provide locks and all on. It's a complicated thing. So you're going to write left paren Zatesh and then some complicated stuff. So you define that as a macro. You say def macro Zatesh. And then you write a description, sort of a pattern of what the different components of this expression is going to look like. And then what it does is you write Lisp code that produces the expression that you want. And so the interpreter and the compiler, then when it sees a Zatesh expression, it'll run this code that you wrote. That will return as its value a piece of Lisp structure, and then either the interpreter will use that in place of the Zatesh expression, or the compiler will compile the result. And so what that means is you always have sort of syntactically meaningful units in your macros. So you don't have to worry that you left off a bracket or a comma or something like that. You're always going to produce something that is at least a list. So,
which is different from C's preprocessor, for example, where you can do anything.
That's right. You can put in anything. In fact, with C's preprocessor, I believe you can define I don't know C so well, so you can tell me if this is wrong, or your listeners can laugh their heads off. I believe you can have the name of the procedure or the function that is returned be constructed from text from multiple files. So you can't even easily figure out what the name of the thing is going to be.
I don't know. I don't know that.
Yeah, so you can't do that with Lisp. So you have this sort of syntactically easy to get right form, and it's through macros primarily that people define these sort of domain-specific type languages on top.
Right. Yeah. So you mentioned at the beginning that Lisp is at its core primarily functional language.
Mm-hmm.
You also said that it has object-oriented notions in it.
Yep.
There is specifically the CLOS or CLOS, I don't know actually how you pronounce it, the Common Lisp Object System.
Yep. Mm-hmm.
So can you talk a little bit about how people got from Lisp to CLOS, and what the differences are, and maybe what flavor of OO it has?
Yep. So there's a long history to this. One of the important early meetings that for object people was, I believe it was in either 1971 or 1972, maybe 73. Alan Kay visited the MIT AI lab, and they talked to each other. And they both learned a lot. Alan Kay was always kind of a Lisp fan, I believe, in the 1960s, and they exchanged a lot of ideas. So at that time, so MIT was a hotbed of Lisp implementation. So they got kind of interested in it. So Carl Hewitt developed the actor language, which is a little bit different from I think there's another actor dialect that came after that. Plasma. There's ideas of combining the functional part of Lisp with the object-oriented part of something like Smalltalk with logic programming. But the real kind of breakthrough of how objects and functions were related came when Guy Steele and Jerry Sussman were trying to understand Carl Hewitt's actor language. So the actor language is a message passing system. And so they figured they could try to understand the concepts by writing an interpreter for a dialect of that, which is very Lispy. So they extended MacLisp to have a language that they were trying to understand what is message passing, what is an object. And that language became known as Scheme.
I was about to ask that, yes.
So it got known as Scheme. And what they did was they wrote an interpreter, like what I just said earlier, this short program. And they thought, well, in order to capture some of the essence of what an object is, what they want to do is an object is really like a function that has no name, perhaps, and it gets as an argument a message, and that it looks at the message and decides what to do. But in their interpreter, they had a separate branch for, is this a function versus is this an object I'm sending a message to? And so they wrote some different code for each, and then as they refactored the code, they didn't have that term back then. When they refactored the code, they noticed that these two versions of eval were exactly the same, actually apply, were exactly the same. Then they realized, message passing is a form of function calling, or function calling is a form of message passing, and objects are a form of function, or functions are a form of object. And so they made that conclusion, but sadly or happily, I don't know, people rapidly forgot that because they thought Scheme was so cool, because it had these called lexical closures. So another concept in Lisp is this first classness. And so that means that anything that exists in the language can be returned as a value, passed as an argument, stored in an array. So you can do that to functions, you can do that to objects. But soon thereafter, a lot of different experimentation went on with different types of object-oriented extensions. So there was loops, there was common loops. I forget all their names. Some of them were message passing. And then someone came up with the idea, with a couple of ideas. One was to, if you have message passing, then you're sending a message to one thing. So if you think about Lisp, and you say, well, message passing is like a function call. So the object is the function, and I'm going to send it a message, and that message is one of the arguments, but you might send it some other arguments. So people started to write methods, basically, and objects that would sort of look at the first argument at runtime and decide which method to use. But when people looked at that, they saw that the method call, the message send, it's invoking the method. If it had more than one argument, it looked like send message to foo ABCD, four arguments. They said, well, Steele and Sussman taught us that the send message doesn't count, so I can take the object foo and make it the first thing, so that's the name of the function. Then you've got ABCD, and the first argument is treated specially. why? Why is the first argument special? So they started to think, well, maybe at runtime you would look at all of the arguments and you would invoke the method that was most appropriate for all of them. And the example they used was, suppose that you're drawing something on a display.
Yep.
So the classical way of doing that is you send a message to the object that says display yourself. So then that thing has to figure out, well, what about the display? Is it a piece of paper?
Right.
Is it a printer?
Yep.
Or is it a handheld device? They didn't have them then. They had handheld devices, but they weren't electronic. So like a spoon and stuff like that. And so they said, well, it's kind of goofy to ask an object to think about a display, even if they could do it very abstractly. So they would say, all right, so I want to define a method that when it's handed an object of this class and you want to display it on a display of this type, then it would just go right to the code.
Right.
So that was called generic functions.
Ah, okay.
And so a generic function is, the arithmetic functions in Lisp are like that. So you can say plus and an integer or an int and a real number, and it figures out what code to run to sort of do the conversion, et cetera, on its own. Yeah. So they just generalized that. So CLOS, which became the dominant object-oriented thing, has that. So it has multi-methods, which are methods that are defined. And then because when you have multiple objects that sort of participate in selecting a method, you don't really associate the method with an object.
With one thing, there's no special this thing.
There's no special this. And so what you do is you associate it with the generic function, which makes sense in some ways. And then ideas that came along at the same time were multiple inheritance. Right. And so that came from a guy named Howard Cannon in Flavors, which is he sort of thought a little bit like aspects are sort of thought of today. There's some kind of functionality that's sort of the main functionality, but you want to add something on. You want to add a lock to some object so that when you operate on it, you want to lock it so no one else can. And you operate and you unlock it. So he invented these mixins so that you could, before you do it, you do the lock, and after you do it, you do the lock. But he didn't want that code to be sprinkled throughout. Right. So he defined these things which are before and after methods, which are kind of what you see in aspects. Yeah. So multiple inheritance was used for doing these mix-ins. So the intention was you would have a main sort of single inheritance hierarchy for your main thing. Yeah. And then if you wanted to have different mix-ins, they would have their own hierarchy. So they would not be blended. Right. But to generalize it, they blended. So they had multiple inheritance, made things complicated.
Yeah. And they would and the mix-ins typically had then this before and after things that would kind of enhance the primary structure.
That's right.
Very elegant, yeah.
And so the terminology they used was there was the primary method, and then there were before and after methods. And again, the Lisp people like to generalize. They said, well, that's just one type of method combination. Right. It's called method combination. So you have before methods that might apply, after methods that might apply, or you might have something that's interposed. So if you have a certain argument, certain object you're sending the message to logically, then you might want to say, well, in this case, instead of using the usual thing, I'll do something instead. And those are called around methods.
Right. Yeah.
So that was called standard method combination, but you could have any kind. So what you could do is you could say, well, if I invoke this generic function, what I want to do is run all of the methods that apply, and and we assume that they return numbers. We'll take the average, or we'll add them up. Cool. So you could define any type of method combination that would examine what methods we're going to use and what the classes were, and it's all part of this sort of metacircular type reasoning. Right. Very elegant, very complicated.
That led to this meta object protocol thing, which we probably would be a separate episode.
Right. Yeah. It's a big topic.
Yeah. You already mentioned scheme, and in the term CLOS or CLOS, I still forgot what you called it.
I call it CLOS. Okay. Most people gravitate to that these days, but CLOS is also used. Okay.
The CL stands for Common Lisp, right? So can you briefly mention which significant dialects or derivations of Lisp exist? Scheme, CL.
Yeah. So the primary ones these days are essentially just Common Lisp and Scheme are the two.
Okay. Yeah.
Back in the 70s and 80s, because of the AI labs, the artificial intelligence labs were separate, There was only a rudimentary internet at the time called the ARPANET. Not everyone was on it.
Yeah.
That meant that every lab developed their own dialect of Lisp. And so there was Lur Lisp and Standard Lisp and MIT Mac Lisp and Stanford Lisp and UC Irvine Lisp and on and on. I could go on for hours, just the names of them. Common Lisp was an endeavor to unify them. So all of those AI-ish type of Lisps became Common Lisp. And so many people liked Scheme because it was small and elegant and it wasn't so side effecty. Yeah, they went off on their own, and so they developed different dialects of Scheme.
Yeah, so I think this imperative stuff you talked about before is something that is more or less in Common Lisp, but not in Scheme. So
they do have it. They do have it, but they don't. It's just downplayed.
Okay.
They try to write in a more functional way. Common Lisp. So the manual for Common Lisp is 600 pages. The manual for Scheme, Scheme just got a lot bigger recently, but up until 1 or 2 years ago, it was like 30 pages, so easier.
Yeah.
And there were some other concepts in Scheme that caught on, so a thing called continuations.
Oh, right, yeah. Hype topic these days in web development.
That's right. Right. So what a continuation is, suppose you're doing a computation, and suppose you're producing a list of things, or suppose you're doing a web transaction.
Right, yeah.
So you might want to sort of return a value now, but reserve the right to sort of go back to where you were.
Right.
And so that's what a continuation is. A continuation is if something gets returned, it's a function. And it says that if you invoke that function on an argument, then you sort of return to where that function, where that continuation was, and you resume.
You kind of save the computation somewhere and go back there. Yeah.
So cookies are sort of a silly way of implementing continuations. So there are some web servers written in Scheme where continuations basically get passed back and forth. You know, they pass tokens instead to refer to the continuations, but the server will hold a continuation, etc.
Common Lisp C-side in Smalltalk does the same thing.
Yeah, exactly. And so Common Lisp doesn't have that. It's another big distinguishing feature. The macros are a little bit different. There's some technical problems that I'm sure the listeners don't want to hear about. But if they want to know what the heck I'm talking about, just Google for or Alta Vista for or Yahoo for or whatever. Hygienic macros, and that'll tell you more than you want to know.
I also think that Lawrence Tratt mentioned that in the episode on compile time meta programming with Converge. He also has something with hygienic macros.
Yeah.
Okay, let's get a bit more practical in a way that we stop talking about concepts and theory. Where is Lisp used these days? And maybe if I were sitting at say, why isn't it used much these days? What's the state of Lisp today?
So Lisp is used, I guess I would say sporadically.
Yep.
It's still used in some, but not a huge amount of AI research. There are some commercial endeavors that are using Lisp. So, for example, what are they called? There's a company in Lexington, Massachusetts. They're called ITA. So I don't know what the ITA stands for. I apologize for that.
Well.
And Dan Weinreb is one of the folks there. They are putting together, and I guess they have deployed an airline reservation system written in Common Lisp.
Cool.
So there's a couple of companies like that. Yahoo Store, sort of this thing that enables people to produce storefronts, is written in Common Lisp. There's some specialized, like some vision. Computer vision stuff is written in Lisp. Some robotic stuff is written in Lisp. And it's just sporadically here and there, but commercially it's still viable. There's still some Lisp companies out there that produce implementations. But it's not all open source.
It didn't catch on as a mainstream. Was it maybe because it is too flexible, too powerful, or is it because it doesn't have curly braces, as some folks say?
Well, there's a lot of reasons for that. And your listeners who are of a certain age will be completely surprised to learn that in the early to mid 1980s, Lisp was the Java of its day.
Okay.
That people, the investment in the business community thought that artificial intelligence was really going to take off with expert systems and all that.
Yeah.
And so the language of expert systems was Lisp, and AI was going to take over the world. And so I believe there was a Business Week cover article about Lisp, and Forbes had articles about Lisp, and I and others were, on radio programs and all sorts of stuff talking about Lisp because
so you're again on a radio program now.
It's happened again. It's come back around. And so two things happened, or two things converged. One was what I call AI winter. I can't remember if I invented that term or Earl Sachadati did. It was during an interview that he and I did, it was kind of like this one, where toward the end of the 1980s, the AI companies were really good at hyping what they could do.
Yep.
And they weren't so good at delivering business results. So a lot of the companies said, well, it's because we're using Lisp. Lisp is not statically typed, and so it's a little bit big. It's a huge, huge, huge language. The runtime for Common Lisp is 3 megabytes. Okay, so your listeners should be laughing now because what is the average size of a Java program these days? 150 billion gigabytes or something. So 3 megabytes back then was considered completely outrageous. Because it didn't have static typing. Static typing was optional in Common Lisp. That meant that the compiler had to produce code that always checked the types, so it would go a little slower. So it was slow. It was hard for beginners to write good code, and so you needed really good wizard level, very expensive programmers. There weren't very many of them. So it was slow. It was big, complicated. Sort of more oriented toward mathematicians and practical people. And all of that kind of conspired for Lisp to roughly disappear for most of the 1990s.
Is there any Lisp hidden in any of today's languages? Is there any worthy successor of Lisp, maybe? Or what's going to happen with Lisp in the future?
I think that you can see the influences of Lisp in lots of places. So Ruby certainly, I think, owns quite a bit.
Meta-programming facilities,
And any of the garbage-collected languages. Lisp had a garbage collector in 1958, 1959, and had garbage collection throughout. And so Alan Kay, said, of course, Smalltalk will have garbage collection. That's been adopted by Java, and that's sort of a major reason for its kind of success, I think, for some types of programmers and some applications. Lisp is used sometimes as an extension language. It's used as a scripting language in some situations. I think in Europe, you can talk to people like Pascal Costanza, folks like that, is getting a little bit of a resurgence, starting to be used for more exploratory stuff in universities and some companies. I would like it to see a little bit of a comeback because it's a very nice language, from my point of view, to do language research experimentation.
Absolutely, yes.
And so I think it might have a little bit of resurgence, but I think its main influence will be through the ideas that spread.
Right. Let's talk a little bit about you. You recently mentioned moved from Sun to IBM. So what did you do at Sun, and why did you go to IBM, and what do you do there?
Yeah, so let me tell a little bit more of the story that might be of some interest to listeners, mostly because it's a fun story for me to tell, and because I like to tell it might sound interesting. So in 1995, for one reason or another, I decided to go back and get a degree in poetry. So that's when I went to Park Place Systems. So I went to school in a low residency MFA program. And my company had failed, Lucid had failed in 1994. And so my plan was I'd go back for a couple of years, get an MFA, and then go back to doing language research using Lisp.
Okay.
So I went off and kind of didn't pay any attention to computer science stuff from 1995 to 1998. When I came back, basically all of my research fields were deleted. That it was no longer possible to do research. There's no place that I could do research using Lisp. There's no place I could do research in Lisp, on Lisp. I couldn't, there's no departments, university departments that would hire me. There were no companies that did it. There were no conferences for it anymore. They all got taken over by the functional programming guys. There were no journals that I could publish in. And you can imagine if you're a sort of an academically minded person to go away for a couple of years and have your entire field deleted.
Yeah, frustrating.
So it was quite frustrating. So at that point I said, okay, well, I'll just consider myself a poet, supporting myself by working in the computer industry. And so Bill Joy called me up, and he wanted me to do some consulting for him. And so Bill Joy is one of the founders of Sun.
Right.
And he had a lab in Aspen called Aspen Smallworks. He had two projects he wanted me to consult on. One was supporting Christopher Alexander implementing some of his new ideas on what he calls the nature of order.
Yep.
So I'd serve as an advisor to Bill Joy, who was funding this. And the second one was to help with this project that Bill Joy basically wanted to become open source. Mm-hmm. So the Alexander thing kind of went away quickly, but then I started to work with Bill and Sun on making this one project open source. And then once that had the success, that is, say, getting that project to be open source, he decided that Sun should move toward open source. Mm-hmm. So I spent, how long was I at Sun? So from 1999 till this last February, mm-hmm. so that's some number of years.
Whatever. Yeah.
I was mostly converting the company to an open source company. Mm-hmm. So learning and teaching about licenses, teaching how to build communities, trying to figure out how companies could participate in open source, because that's really not like what sort of open source was about. Yeah. Teaching management, coming up with business strategies. Eventually, my colleague and I, Ron Goldman, wrote a book on that, which is it's sort of like a handbook for businesses on how to do open source and what it all means.
We'll put a link to it in the show notes.
And so being an open source book, it is available online for free.
Great.
But you can also buy it. So there's a I'm not sure there's a PDF of it, but certainly a HTML version of it that's easily available. Mm-hmm. And I think open source books have to be that way. And when we sort of succeeded, when Ron Goldman, the co-author, and I succeeded in that, we went back into Sun Labs and to work on some research on keeping, so we call it self-sustaining systems, mm-hmm. How to kind of marry traditional programming with some biological concepts to sort of keep programs alive, to sort of solve some problems on both sides of that equation. Mm-hmm. Sun Labs is a very old-fashioned type of lab. It's a very engineering-oriented lab. Mm-hmm. And they were not as friendly, I would say, toward a project that was very expansive like that. Yeah. So it just felt a little bit like they liked what I was doing, but I just felt like maybe I should be somewhere else. Mm-hmm. So I liked Sun a lot, and so in February of this year I moved to IBM Research, mm-hmm. where I think there's a little more freedom. It's a little bit bigger company. There's a little bit more resources. Yep. They seem to understand. So I was the general chair of UPSLA. Now they mentioned 128 weeks. So if you do the math, that's like more than 2 years.
Yeah. You mean that was full-time?
So it was full-time for me for the last, since June 1. So July, August, September, October, November. 5 months of full-time. Mm-hmm. 5 months of half-time to three-quarters time, and then the rest of the months were about 25% time. So that's a big.
Yes, absolutely.
UPSLA is complex. I'm sure you've been gathering that from these interviews.
Yeah. And you're working on this ultra-large-scale system stuff.
Right. So
we've had an episode on that already.
Yes, that's right.
Before.
So a couple of years ago, I joined this task force that was looking at task force sounds like a really military thing, but a study group for ultra-large-scale. So what would it mean to have a system of 1 billion lines of code, for example? And how would you put that together? And would there be an architect? Could there be a single mind that conceived of it? Yeah. So I work on that. I work on some of the self-sustaining system stuff, and I do some public service things like UPSLA.
Cool. So to wrap this thing up, do you want to briefly talk a little bit about your poetry side and how you think poetry, literature should go or should be of more importance in the software field and this kind of stuff?
Yeah, there's a couple of aspects of that. When I didn't have a literature background when I went back to school. Mm-hmm. And learning writing and sort of learning about creativity was not what I expected. And the thing that was surprising about it is that it can be taught, more or less. And it's taught by a way of teaching and not by the subject matter, not content that's sort of thrown at you.
Right.
And the way you learn is it's sort of creating and revising and examining other creations while reflecting, while thinking about it, while writing about what you're doing and what you see. And the other thing that I found out was that creativity comes from having a sort of a diversity of ideas and a background, putting together, synthesizing things. And I think all of that applies to science, that the methods of teaching, the way you teach writing, that you teach art, should be used for teaching design, software design, and stuff like that. So I've been working a little bit on creating an MFA of softwares or MFA of design for that. Also, I think a lot of the ways of doing exploration, this whole concept of getting lost in order to discover, I think applies to the work we do as technologists, engineers, and I think it's quite informative.
Yep.
Writing poetry itself is quite an interesting enterprise because you need to open yourself up to a type of observation that you can learn how to do that is not that commonly used or not consciously used in the software world or the computer science world. The way I'm sort of starting to talk about it these days, it's sort of the influence of chaos on reason. So, so going back to sort of an AI way of thinking about things, imagine you had a theorem prover that was trying to reason about chess or doing something like that. And running at the same time and the same address space was this sort of rapidly associative program that just sort of every time the rational part was sort of trying to prove something or looking at a concept, then this other thing would shout out anything that was related metaphorically or sort of linked together. That's what creativity in the poetry world feels like, that there's this chaotic thing that's going on that you sometimes pay attention to and it just informs you. So I'm trying to sort of spread that idea and get other people to work and think that way because I think it would help them. So that's the thing. The other thing that's interesting about it is for the last 7 years I've written a poem a day.
Cool. Yeah, I've seen that on your website.
And so in the poetry world, the idea of writing a poem a day for a week is more than most poets can bear. Writing a poem a day for a month is considered impossible. There's one or two people who have done it for a year and doing it for 7 years in a row.
Quite a bit of work.
I've gotten to a place in what it's like to write poetry. I'm not a great poet. That the poets that I know who are good poets see, when I talk about my process now, it's so different from what they do that they want to understand it because no one has gone that far with it. So
we'll put a link to some of them.
Yeah. So I think that there's, I think that scientists and artists need to get together more and sort of help each other out because we're all interested in the same things ultimately.
One last thing that's maybe worth mentioning is that I think it was you who introduced the writer's workshop concept known from literature into the patterns communities.
That's right.
So that's another kind of cross-bleeding of these different worlds. Okay. Thank you, Dick.
Well,
anything else you wanted to say before we shut this down?
I really enjoy Software Engineering Radio. As you know, or your listeners know, we used you for doing some podcasts for Oopsla.
Thank you for making that possible.
I just love the way you do this.
So that is, of course, really good to hear. Thank you, Dick, for these nice words, and thank you for the interview. I know you have been very busy at Oopsla, and you still found the time to talk to us. Thank you very much. Before we shut down this episode, I want to play a song. It is called God Wrote in Lisp. It's obviously about Lisp. I've gotten to know this song during a talk Dick and Guy Steele gave at Oopsla. It was called 50 in 50. It was about 50 different interesting features in 50 programming languages over the last years. Really, really great talk. Standing ovations at the end. So the song I'm going to play is from the Roundworm album by Prometheus Music, and Ellie Goldberg from Prometheus Music allowed us to use it on the podcast. It's performed by Julia Eckler, and the lyricist is Bob Kanevsky. Have fun listening to it and talk to you at the next SE Radio podcast episode. Bye.
construction work with a toothpick for a tool. So when I made my senior year, I threw my coat away and learned the way to program that I still prefer today. Now some folks on the internet put their faith in C++. They swear that it's so powerful, it's what God used for us. And maybe it lets mortals dredge their objects from the sea. But I think that explains why only God can make a tree. For God wrote in Lisp code when he filled the leaves with green, the fractal flowers and recursive roots, the most lovely hack I've seen. And when I ponder snowflakes, never finding two the same, I know God likes a language with its own four-letter name. Now I've used a sun under Unix, so I've seen what C can hold. I've searched for pearls, found what Fortran's for, got that Java stuff down cold. Though the chance that I'd write COBOL code is a snowball's chance in hell. And I basically hate hieroglyphs, so I won't use APL. Now God must know all these languages, and a few I haven't named. But the Lord made sure when each sparrow falls that its flesh will be reclaimed. And the Lord could not count grains of sand with a 32-bit word. Who knows where we would go to if Lisp weren't what he'd preferred? And God wrote in Lisp code every creature great and small. Don't search the disk drive for man.c when the listing's on the wall. And when I watch the lightning burn unbelievers to a crisp, I know God had 6 days to work, so he wrote it all in Lisp. Yes, God had a deadline, so he wrote it all in Lisp.
Thanks for listening to Software Engineering Radio. If you want to get more information about Software Engineering Radio, or if you want to give us feedback, please go to our website at se-radio.net. You can also contact the team at team@se-radio.net, although we prefer entries in our comments system on the website so other people can see what you think. Software Engineering Radio wants to thank Henning Pauli for the intro and outro music, as well as Libsyn for providing the bandwidth. This episode of SE Radio, as well as all other episodes, is licensed under Creative Commons license. See the Software Engineering Radio website for details.